In last week, we had a very brief introduction to semiconductor industry. And today, I would like to tell you some kind of introduction about analog IC design. Especially, we need to differentiate the difference between the digital and the analog world. As you know already that humankind already digitized almost everything, our video, our audio, everything, almost, into digital domain. So under such kind of circumstances, why we still need analog chip design? That is a big question. And why you are here? Why don't you take the other class related to digital chip design? Okay, I am not talking about digital chip design is not important, no. But I would like to tell you why humankind still focus on analog design very much. And this is the later part of our chapter 1, and it is from Professor Razavi's design of analog CMOS integrated circuits, the first chapter. Yeah, I have some kind of very brief presentation about this chapter. Anyway, from the very beginning, you need to make sure analog is good for you. But why? According to almost everything digitized, why we still need analog design? Actually, digitization means that we would like to transfer something from the analog world into the digital, right? We need something called interface. Yeah. So who can help you to do such kind of digitization? Digital IC designer? No. Analog IC designer. All right? So to interface, to bridge both worlds, I mean, never mind from analog to digital or backward from digital back to analog. The only guys can help you to be analog IC designers. Because for digital IC designers, usually they never touched anything related to analog. But how about us? We need to focus on everything. Okay? Yeah. So the first reason is to process natural signals. All the signals you have, you can listen to, you can watch, not only for you, yeah, but also for the dogs, the cats, the pets, everything. Humankind or even animals can feel. That is in analog domain. You need to be very, very careful. Okay? Nothing is in digital. Yeah. If you, for example, you have some kind of audio file, video file, if you open the file to have a look, you can only see 0 and 1s. I don't think you can enjoy anything like that. Okay? Our human eyes, our skin, our body, our ears, nothing related to this. Everything in human sense, in animal sense, is in analog. That is the most reason why. But we need to do the interfacing, right? From the analog domain to digital domain. So we need this, ADC, analog to digital converter. And vice versa, if you would like to convert it back, just like all the files you download or you watched online, right? How about the information inside? Only 0 and 1s. But I don't think you can enjoy it. You need to watch it. You need to listen to that. How? We need to convert back all the 0 and 1s to natural, I mean analog signal in audio domain, in video domain for you to enjoy. Okay? So from analog to digital, we call it ADC, right? Analog to digital converter. Backward DAC, DAC, digital to analog converter. Yeah, anyway, we need substantially such kind of data converters. I think in your smartphone, maybe more than 10, okay? A lot of data converters inside, even in a smartphone. Yeah, so we use such kind of data converters substantially. Again, Who can help you to design such kind of data converters? Only analog IC designers. Okay, because again, for digital IC designers, they only focus on two issues, zeros and ones, not the others. All right. If you ask me in signal, what is the major difference between analog and digital? Very easy. Okay? In digital, their word is black and white. Either black or white. That's it. Nothing inside. Nothing in between. That is their word. But in between, it belongs to analog. Almost everything. From 0 all the way to 1. So we have the so-called gray level style. We have colorful life. Our life is colorful because from 0 to 1, everything is possible. And for theirs, they are only black and white. That is the major difference. And this is the reason why they cannot help us to design any kind of data converters, because they know nothing about 0 except for E0 and 1. Okay? In between, they know nothing. That's it. Since they know nothing in between, for them, they cannot do any kind of help to you. Yeah. Maybe you can say, hey, in their world, they have not, for the real signal, they have not only 0 and 1, right? So they have a very easy rule to differentiate between 0 and 1. They have the so-called threshold voltage. Above it, that is 1. Below it, that is 0. That's it. Okay? So never mind what's here, what's there. Only if above the threshold, all those will be 1s. Below it, all those will be 0s. Their life are supposed to be much easier than us because we have a lot of noise interference. So ideally, you have 0 and 1, but in practice, you have many kind of noise interference to change the waveform, right? But for them, above it, 1, below it, 0. Bingo. They have the so-called data regeneration. 他们的资料可以重生。Okay? Yeah, for us, nothing you can regenerate in analog domain without lose some accuracy. Okay? That is a very sad life for us. But you can see circuit is harder to design in analog domain. And that is the bad. Okay, but that is also the good for you because you can ensure your future. Nobody can replace you, especially, I told you, AI. Okay? For digital design, sooner or later, yeah, I cannot say all of them, but some of them, or even many of them, will be replaced by artificial intelligence. And how about our analog design? In the near future, 0. Yeah. And in the long run, I have no idea, but I can promise you, we won't be replaced 100%. No. Okay? Yeah, that is one issue. And also, for example, from the sky, we need to receive the signals, right, from the base station. Yeah, so right now I'm talking about RF signal. How large the signal is, usually microvolts. Okay, but if you would like to look at, or you would like to listen to, how much the amplitude should become, usually volt. Okay, I mean, yeah. The order of volt, point something or 1.2 point something, yeah, that's it. Okay. So from the signal in the air to what you can look at or what you can listen to, how much you need to amplify? Almost 6 order. Okay. You need to amplify the signal with 6 order, 6 zeros. How can you make that? First of all, we need amplifier, right? But especially LNA, low noise amplifier. Why? Because the signal is really, really small. if your amplifier itself is really noisy, right? Then the amplifier not only amplify the signal, but also the noise. It's really bad. Your signal will be buried by the noise, 会被杂讯淹没. That is really, really bad. So first of all, you need to make sure your amplifier without too much noise. That is the concept for LNA. Okay? That's it. Who can help you design LNA? Sorry for that. Only analog IC designers. All right? If you talk this kind of signal, I mean the magnitude of only microvolt to digital IC designers, they will be scared. What's that? That is zero, right? According to their definition, yeah, it means nothing for them. But we need to amplify from 0 to 1, okay? That is our duty. That is our responsibility. Yeah, make it. If you make it, then again, your future will be insured. All right? After such kind of amplification, if the signal becomes large enough, then we need the others called filter. Yeah. What is the function of filter? Very easy. To take anything you dislike off, only preserve something you need. Okay? That is a very easy concept for filter. All right, but usually we focus in frequency, in frequency band. So from the very low frequency to very high frequency of gigahertz or something. Now, if you would like to keep the low frequency one, then we will say, oh, that is some kind of low pass filter, LPF, right? If you want to only preserve the medium one, oh, band pass filter. Or if you would like to only keep the high frequency one, oh, congratulations, that is a high pass filter, blah, blah, blah. Again, if you talk anything like this, low pass, band pass, or high pass, I mean in frequency domain, wow, it will be scary again to digital IC designer. But allow me to point out that we have trained, I mean between analog and digital part. This is in analog domain. Yeah, we focus on frequency domain and how to apply the circuit mechanism to filter out all those noises into frequency you dislike, okay, or frequency band you dislike. In analog domain, we have a similar, the twin, the brothers of our design. Yeah, we call it from DSP, right? Digital signal processing. We have digital filter design. Yeah, that is totally different from our own, okay? Again, for implementation, it is easier, all right? But for theoretical study, that is another story, because for such kind of DSP, I think you need to study more mathematics, more theorems, all right? And that is the difficult part for analog IC designers. Usually, analog IC designers are afraid of equations. That's it. I have no idea why. And how about the digital IC designers? Again, most of them are afraid of theories, equations. So we need the help from, yeah, mathematicians or somebody to help us develop all those theories. To be honest, who help us to develop it? The guys from communication, telecommunication. Okay. Anyway, it is not developed by digital IC designers. No. And then we can focus on this. Hey, I'm a digital guy. I look everything online, right? Everything in the phones. All those are in digital domain. Yeah. Okay. If you would then like to have any kind of issue related to analog, you still need to transfer your digital signal from here to there, right? If you listen to the online radio, yeah, all those information transmitted should be in the so-called digital domain. Okay, so even though somebody is a digital word lover, okay, he or she wouldn't like to touch anything about our analog domain. Anyway, there is still a need for digital communication. Yeah, you need to share with each other all those digital information. But how? For example, in the past, we have such kind of wild communication. Okay? 有线通讯. Who is the king? Broadcom. Broadcom actually was the best, maybe even is the best for wild communication. So in the past, something like ADSL, right? Most of them are dominated by Broadcom. It's too successful. So it didn't pay too much attention to wired communication. So some years later, for wireless communication, there was another king called Qualcomm, right? Yeah, that is a really sad story for Broadcom, because again, it didn't pay attention to wireless communication. After some years, yeah, this one became the king, and the market size for wireless communication became much larger than wired one. All right. So in telecommunication field, the overall king is Qualcomm till now. Even Apple has a big problem with that, because it is the king. So it is the rule maker. It set the rules for everybody. I would like to collect how much money according to myself. Okay, only if I'm happy, then you need to be happy, because you don't have any other choice. Okay, I set the rule, follow me, or out of the market. That is what the rule can be set by the king. All right, so even Broadcom have no say in this domain. Yeah, again, wired communication right now is much, much smaller than wireless one. A very sad story. Anyway, even you only look at about such kind of wired communication, you need to transfer such kind of digital content, digital data through wire to the other place. Yeah, from the very beginning, you have something like this, only 0 and 1. So be happy, right? 1 0 1 1 0 1 0 0, blah blah blah. You can see it clearly, but sadly enough, nothing is perfect. All right. After wired communication, because the wire, the cable, is lossy. It means what? It has some parasitic resistance. It has some parasitic capacitance. Okay, so after transmission, finally, you will get something similar to this. Then tell me, what is the result? What is the original content you would like to get? If you get such kind of signal, forget about it. You have no way to know what's the real content from the transmitter. This is from transmitter side, and this is what you get at receiver side. Can you get something? No, only nothing. So what is the problem about wired communication? According to the resistance, capacitance inside, you cannot transfer too far, or you cannot transfer too fast. That is the problem. All right? Anyway, according to RNC, we get something very similar to low-pass filtering. The high-frequency components will be filtered out. Okay, so where are the high-frequency components? here and there. You have something perpendicular to each other, right? That is a high frequency one. They will be smooth. So you will get something like this or that instead of this and that, right? The longer, it will become smoother. The higher frequency, the more serious impact. That's it. Okay? What are you going to do? Nothing. For wired communication, except for fiber communication, that is another story, because the signal is transmitted by light instead of electrical voltage or current. Except for that, everything for such kind of wired communication, there is some kind of inherent limit for humankind. To my memory, sorry, megahertz. 33 megahertz. Nothing better than that. Okay? I'm not talking about long distance transmission. No. In the past, even inside personal computer, you need to connect your hard disk to your motherboard, right? Or your DRAM to your motherboard. How fast? Sorry. From the beginning, 33 to the end, 66. But how? We need to some kind of shielding. For example, D0, then grounded, D1, then grounded. Okay? With such kind of shielding, oh yeah, you can double the transmission rate from 33 to only 66. Nothing more than that. It's really upset. That is also for the so-called parallel communication. Okay? Yeah. No much better than this. Okay? Even on board, on your PCB, on your motherboard. Wow. So how to increase the transmission speed? Usually from parallel to serial. Okay? 从并联通讯到串列，一次只传一个 bit. That is the idea. From multiple bits to a single bit. With single bit communication, that is so-called serial communication. You can increase the speed up to more than quite many gigahertz. Or even right now, more than 10 gigahertz, especially for Ethernet. Okay? Again, wow, for serial communication, humankind can make for more than 10 gigahertz. And how about parallel one? Again, not much more than 66 megahertz. Wow, it's really upset. And why? According to clock skew, that is another story. Why? It is limited not only by the noise interference, but also a very serious problem. We call it clock skew. 时脉歪斜. And what's that? If I have time, okay. Not for the first class, for introduction. All right, anyway, if you would like to get further, I mean, you would like to transmit the digital signal, I mean 0 and 1s, for a longer distance or higher frequency, what you can do? Okay. There is one of the ways out. What's the difference? We transmit 2 bits instead of single bit. Okay? At a time. So what does it mean? For the same content, you can see the same content here and there, but from the very beginning, humankind transmit 1 bit by the other, bit by bit. 1 and then 0 and then 1. But if you would like, you can transmit 1 0, 1 1, 0 1, 0 0. But what's the difference? All right, in magnitude, yeah, you need to have, because in the past, 1 bit means only 2 possibilities, 0 and 1. That's it, right? Right now, 2 bits, 2 to second power. You need to have 4 levels. Bingo. So the minimum 0, 0, the highest 1, 1, blah, blah, blah. Okay? And then, because you transmit 2 bits at the same time, so the duration for such kind of transmission is doubled, right? Doubled means what? You have a longer time. Longer time means what? Lower frequency, convergence. Okay, so the parasitic R and C does less hurt to such kind of low frequency signal. Okay, got it? So after transmission, supposed to be you will get better result than this. Okay, and this is a very important idea. Yeah. Right now, because we transmit not only 1 bit, multiple bits, we call it a symbol. That is what you can learn from communication or telecommunication. Okay, so they transmit symbol by symbol instead of bit by bit. But in each symbol, it depends on your modulation. Yeah, here 2 bits. Sometimes we have 4 bits or even more. For example, if you have 42 QAM or something, 64, sorry, QAM. So what does it mean? 2 to 8 power. Each symbol means 8 bits. Okay, and also that we have the so-called, according to communication theory, we have the so-called Baud rate. Hopefully my spelling is correct. Baud rate. Yeah. Baud rate means what? How many symbols you can transmit per second. Okay? Usually that is much larger than bit per second. Okay? Here, your baud rate is, yeah, once how many symbols per second, right? It means double by your bit per second. That's it. Okay? That is one of the major secrets for communication, how to increase the throughput for our telecommunication. Yeah, they transmit symbols. Okay? Yeah, anyway, in this way, yeah, you can get better throughput. But nothing is free. You need to pay for it. How to transfer multi-levels? From the beginning, you need DEC, right? According to 0, 0, the minimum, 1, 1, the highest. Oh, okay, yeah, as you like. But yeah, we need DEC. That is at the transceiver side. And how about the receiver? It needs ADC. Yeah. Oh, the highest will be mapped back to 1, 1. Yeah. Here 1, 0, 0, 1. Blah blah blah. Okay. Again, with such kind of symbol transmission instead of bit transmission, nothing can be done in digital domain. You need DEC and ADC. It means according to our analog IC designers. Okay, nothing related back to digital chip designer. Not only this, but also, for example, hard disk driver. Okay, forget about it. Why? Because I don't think right now anybody use any kind of hard disk. You usually use SSD, right? Solid state disk. So forget about it. But anyway, we still rely on wireless communication very, very much. So for such kind of wireless receiver, this is the band for you. Oh, this is mobile phone. In the past, we call it GSM or something. Oh, I forgot the communication standard. Anyway, never mind. From 2G, 3G, 4G, and into the future, or even now, yeah, somebody like Samsung, Huawei, LG, many of them announced their 5G mobile phones already, right? Anyway, how about the band? The band for communication, I mean the frequency band for communication is still there. Not much larger. Yeah, for 5G, we will focus on different frequency bands. But anyway, never mind 2G, 3G, 4G, any kind of G. Yeah, we have some band to be shared by all the users, not only in the class, on our campus, or even in Taipei City. Oh, not so big. We have the cellular zone. Inside each zone, you need to share the same bandwidth. Okay, thousands of people inside. So, do you have thousands of mini bands inside? No. We need to reuse. Okay, but anyway, since the band is very precious in Taiwan for 4G, I guess you need to invest for each company, tens of billions of NT dollars to share the band, not to occupy the full band. No. Okay. And how many companies, telecommunication companies here? At least 5, I guess, 5 or 6. All right. So totally, I guess the government get more than 100 billions only for the bidding of such kind of frequency band. Wow, the government can make a lot of money from that. All right. So for the companies, they need to make money from you, right? So each time they only allocate a very little band, very small band for you. Okay. You need to share with each other. So this is my very small band, and that is your very small band, blah, blah, blah. Because they are really small and close to each other. This is myself, and that is you, right? Your signals will become my noise, my interference. I need to filter it out. For my own phone, I need to focus on this and kill all the others. Who can help you? Usually, especially in such kind of high frequency operation, nothing can be done in digital domain. Okay, no. Even with DSP, you cannot make it. In this way, you need to filter the interference exactly in analog domain, especially for such kind of very high frequency band. Yeah. So there are many issues for you to concern in such kind of analog design. The noise, the frequency of your operation, and out of that, it will become the interference. How much power you need to take and how much cost. All of them are your challenges. Yeah. Again, I need to point out that don't expect yourself will get the minimum noise, to kill all the interference, to dissipate the least power, and get the minimum cost. No, forget about it. Okay? If every time your logic thinking like this, I promise you, the best result is over design. And what is the worst scenario? You will fail. You cannot design anything. That is the worst scenario. And how about the best scenario? Oh, bingo, you make it, but for over design. Right? Over design is not so bad on campus. To be honest, you can publish papers to say, hey, I'm the king of the world about this or about that. Yeah, as you like. But anyway, for companies, they hate this very much because for over design, it usually means large chip area, more power consumption, higher cost, blah, blah, blah. So you need to train yourself, especially for not over design. Okay, no over design. is a very good idea for engineers working for companies. And then sensors. Wow. We have a lot of sensors even inside the smartphone. Okay. What kind of sensors you have? A lot of that. For example, you have G sensors. You have temperature sensors. Okay. You have light sensors. For example, if you talk to the phone close to your face, right? The screen will be turned off automatically, right? How does it know your face? No. They have some kind of light sensor. Yeah, it emits some light, reflected back to the receiver, right? If it is closer, then the receiver will get higher brightness, higher response. Then over some threshold, the smartphone will turn off the screen to help you save some power. Okay? We need, I guess, right now more than 20 or 30 sensors inside. Again, what to sense? I told you already, anything related to sense should be in analog domain instead of digital. No 0 or 1. No, 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 no. Everything in between 0 and 1. Okay? That is the function of sensor. Anyway, a very simple definition for sensor is to convert some kind of physical quantity from A to B. That is the definition for sensor. For example, temperature sensor. Oh, we convert physical quantity called temperature into what? Voltage or current. Okay? Yeah. And how about the pressure sensor? The air pressure? Yeah. Okay? Yeah, we have some kind of air pressure sensor. Yeah, to convert the air pressure into what? Again, voltage or current or capacitance, anything. Okay? Yeah, especially you can guess. All right, we have some cavity. Yeah, and some membranes, okay, above it. The higher pressure, air pressure means what? You will get more diffraction, deformation. What does it mean? The capacitance between the membrane and the cavity will be increased because you know, right? The distance between the membrane and the cavity will be reduced with higher air pressure. Blah, blah, blah. Okay. That is one kind of air pressure sensor. Oh, we have quite many sensors anywhere. Yeah. So only if you convert A physical quantity into the other B physical quantity, who cares? That is sensors. But usually we convert something into voltage or current. And then, even you get voltage or current, it cannot be processed by your smartphone. It is smart. So it means what? It can only help you to deal with 0 and 1s. I mean, digital signal. So we need the help of ADC, right? To convert the voltage, the current into digital domain. Wow, that is really difficult. Anyway, we have another definition for smart sensor. How to make your sensor smart? You need to make the output become digital. That's it. Okay? Stupid sensors means into analog something. Yeah, smart means into the output should be digital. Then it can be processed by your smartphone, your smart devices. That is the definition for smart sensors. Blah blah blah. Yeah. Anyway, allow me to tell you some of the interesting sensors. We call it accelerometer. Okay, acceleration meter. What does it mean? 加速计. Okay, what is the function? What is the usefulness of such kind of sensor, accelerometer? It is used. One of the main purpose in the past is used to control the popping up of your airbag. When you drive on the road with very fast speed, then bump with the other one, right? Oh, to protect yourself, the airbag needs to be released, needs to be popped out, right? Bingo. How can we sense such kind of critical conditions? Here is the function of the accelerometer. Yeah. If you go, let me think, in this way, right, with very high speed, then collide with the other car or collide with some kind of building anyway. Okay, according to the momentum, we have for the first version we have two plates. One is fixed, the other one is deflectable. Okay, so for the fixed one, it is fixed. It cannot be deflected or moved. So after collision, only this plate, according to momentum, you keep on going. This one is fixed and the other one, okay? Then again, the capacitance here will be increased, right? So in theory, the controller of your car monitor the effective capacitance of this one to make the decision whether or not to pop out the airbag. Okay, very easy, very simple. And then many of the rich men were killed on highway, especially in the United States. Why? Because you need to sense the variation of such kind of capacitance around about 1% of such kind of deviation. The controller needs to make the decision whether or not to pop it out. 1% means what? Really hard to sense, right? Sometimes you hit something, no popping out, you are killed. And sometimes, especially on the highway, if you run over a small stone, right? And the car will, especially at very high speed, the car will vibrate. For such kind of vibration, oh, sorry for that. You will get something over this limit, right? Then the airbag will be popped out by mistake. And then you cannot see anything because it's too huge, right? Wow. So this is the reason why many of the rich men in the United States or even in European countries were killed by accident. It's really ridiculous. 1% to make it or not too dangerous, right? So we have the second version. After the sacrifice of many human lives, we try to redesign it to become this. That is a better idea. You can see right now we have two fixed plates and the same deflectable plate in the middle. Okay, if nothing wrong, if you drive the car at constant speed, then C1 and C2 will be exactly the same, ideally. But after you bump here or you bump there, it will be deflected to the right, to the left, or to the right. Okay? Then you only need, for our circuit, we only need to sense the difference. So it means what? From minus 100% to positive 100%, you have a lot of space to make your own decision whether or not to pop out the airbag. Okay? So from the beginning, I mean for the first generation, we depend on the absolute value of the capacitance within 1%. You need to make it too dangerous. But right now, we focus on the difference, minus 100 to positive 100% for you. Congratulations. Much, much more safer. Okay, so since after, nobody used this. Even though if you are the company to file the patent by this, then the other company modify it, right? Modify your patent to get a new one. Does it violate your patent? Yes. Yes. But it gets more functionality. It becomes safer, blah, blah, blah. Okay? So it can also apply another new patent. But even though it violates yours, it can still get a new one. And then you can go to the company, hey, come on, pay me something. But to promote innovation, our system is, I mean for Western countries, for Taiwanese system, or instead for Chinese, okay? They can copy and paste for nothing. But if you respect the worldwide rules, such kind of new pattern can dominate the market, and you only need to share maybe less than 10% to the original company, okay? Okay? What I would like to tell you with such kind of example is, if there's some pattern in the market, the best way is not to get rid of all the ideas. No. The best way is to add something more to enhance the performance. Then you apply a new patent, even though it violates the original one, but according to our system, you need to pay only very little to this one. Now you say, hey, if I can, try to, how can I get rid of, I wouldn't like to apply any idea from this. Oh, if you can make it, congratulations, you pay 0% to this company. But it's really hard, okay? Really, really hard. So the easiest way, the best way is still to modify, get something more, or reduce something. Are you right? If you can reduce something to get the same result, congratulations, you don't violate it. Okay, because one of the rules for such kind of patent assessment, 专利鉴定 is you need to have all the components here. Okay? If they have A and B and C, blah, 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 and you figure out, oh, I don't need to use C, but I can still achieve the same purpose, the same function. Congratulations. Because according to such kind of completeness, you don't have everything from the original one. Congratulations. You don't violate the original patent. Okay? But again, it's also really, really hard. So usually, we add something more. You have A and B and C. Then I get one D, okay, to apply for new patent. That's it. But you need to be very careful. For example, if you have a cup, right? Some patented cup, and you say, hey, according to Professor Chen's idea, then you have something attached to here for nothing. Okay, hey, you have A, you have B, and I get another C. Oh, I can apply for a new patent. No. Why? Because the new one you added to this doesn't create any new function. Okay? It doesn't enhance your performance, blah, blah, blah. Then we are not fools. We are smart guys. If you add something for nothing, then you cannot file the patent. Okay? That's it. That is what I can tell you. Anyway, you will say, hey, I'm AI designers. I only need to use computers, right? Softwares. Anyway, I don't need to care about analog design. No, 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 no. Even for those guys, for AI guys, they still need to use microprocessors, memories, everything, right? Even, who is the best for microprocessor? Intel. For mobile cores, ARM, right? For memory, Samsung, blah, blah, blah. Okay, allow me to tell you that Intel focus very much on CPU design, right? But Intel hires more than 50% of the engineers for analog design instead of for digital. Okay, many of the humankind think, oh, CPU memories belong to digital domain. But sorry for that. Even for Intel, the king of CPU, right? It hires more analog IC designers than digital one. All right? And this is the reason why analog design is very, very important. Okay? Are you happy? The class is good for you, hopefully. All right. Oh, okay. One more slide. If you're happy, if you would like to learn something about analog IC design, then you need to ask yourself what kind of personality, kind of skill you need to have, what you are required to be a good analog IC designer. First of all, I need to tell you that you need to be very good at microelectronics, because all the circuits we have in analog IC design actually come from microelectronics, and we do some modification. Okay, so if you are not good at microelectronics, supposed to be you won't be good at analog IC design. So what you can do, go back to read your microelectronics. Okay, fully understand the content. You don't need to derive anything. No. You read all the text, get full understanding. Good enough. Okay, and then this is the most fundamental. And then you need hard working to get better experience. Okay, so this is as you sow, so shall you reap. 要怎么收获就要怎么栽. Okay, and then after that, innovation is the key. You need to be very innovative. Yeah, in this domain, IQ is not everything. In digital domain, I promise you, the smarter, the better. Okay, in our domain, the smarter usually don't mean the better. Why? Because smart guys believe in themselves too much. But what you see is not what you get in this domain. If you believe in yourself too much, you will believe in what you see. Good enough. After fabrication, sorry for that. Okay? There is a lot gap between what you get and what you see during design, especially for your post-simulation. This is for your post-simulation. You see, wow, very good. And what you get after fabrication, usually nothing. Okay? You need to get enough experience, know-how to make what you get good enough. The learning curve in analog IC design is really, really, really long compared to digital one. That is a big problem, but yeah, again, it ensures your future. Okay? Yeah, the learning curve for digital one here, for analog one there. Yeah, at least 5 years in difference. If you go to analog IC design houses to be the team leader, I guess at least 5 years. Okay? To become some kind of manager, usually more than 10. Yeah. And after you make it, nobody dare fire you. Yeah. Anyway, the longer you live, you get better pay, okay? And then, this is to ensure, by hard working, by innovation, you can ensure your future. But in digital domain, almost everything is decided by your brain. How smart you are means how good you will be. That is the usual case, okay? But that is not the usual case here. Hard working still means something in this domain, I mean in analog IC design. So allow me to test you how innovative you are. Do you know some kind of monitor, monitor company called ViewSonic? Oh, if you say yes, it means you are a little bit older than the others. I'm only kidding, because I have no idea whether or not ViewSonic is still in the market, okay? This is something called ViewSonic. In the past, when I was young, that is almost the best monitor in Taiwan. It's really expensive, right? In that era, we have no brand monitor. The monitor without any brand. So some of the guys, raised 3 birds. Allow me to zoom in for you. Oh, it looks similar to that. That is the cheapest way for you to upgrade your no brand monitor to a ViewSonic one. If I figure out somebody like this, I will recruit him or her to be my students, because innovation. Okay? And this is the other very good story for you. Tens of years ago, Toshiba, right, had some kind of problem with the electrical fans. In the past, Sony dominated the market, okay, for such kind of e-fans, electrical fans. Toshiba produced a lot of fans, but couldn't sell to the market. The market share is really small. So the CEO felt really upset. Once upon a time, he called all the employees, come on, if anybody can help our company sell out the fans, I will offer you how much? 10% of the stock share of the whole company. Okay? Okay? When Toshiba was small in that era, it would like to compete with Sony for electric fans. But how? They tried their very best to produce the fans with very good quality, blah, blah, blah. But people only believe in Sony. Again, Sony is the king in home electronics. Okay? How can you compete with Sony? Nobody would like to buy your fans, because if they have money, they buy Sony fans. They wouldn't buy any Toshiba fans. One of the employees figured out a crazy idea. I have no idea, a male or female. Anyway, the employee told the CEO, why not we have colorful fans? Because all Sony fans were black, right? Why don't you change the color? You just copy and paste Sony's design, all in black. Consumers may need the other colors. Okay. Oh, why not? So they changed the color. Wow. And then sell all the fans to the market. The market share becomes sky high. Congratulations. The employee get 10% of Toshiba. Toshiba, not HTC, right? 10% of Toshiba stock share. Wow. By what? Hard working? No. By innovation. How innovative? Change the black into yellow, red, white, anything? Not it. To get 10% of the stocks. That is what you need to encourage yourself. To be innovative is always the key issue in analog IC design. And before the break, allow me to show you something even more fantastic. What's the story here? A mother tiger, right? with many baby cubs? Pigs. Exactly. Do you know why? That is also a very inspiring story. In some kind of Chinese zoo, the mother tiger gave birth to many baby tigers, but all of them passed away, right? Due to some kind of maybe DNA issue or something. So the mother tiger has a big issue, big problem. It got very serious postpartum depression, 产后忧郁症. Wow. So it wouldn't like to eat anymore. It becomes very, very sick. So how can we do? Some of the employees, wow, get some kind of crazy idea. Use some kind of baby pigs with tiger skin. Tiger clothes. Wow. After that, the mother lived happily since after with the baby tigers. Okay? Innovation. I would like to recruit the employee. But I have one question. After the piggy grows up, right? What will happen? No idea. Okay, sorry for that. We can have a break for all of you to copy the slides here.